Ma'am, I have a few doubts in the doubts, ma'am. Could you please, can I mail it, ma'am? I need a doubt clearing session. Can you arrange one more session, ma'am? Doubt clearing session specifically.
Maybe you can ask your doubt here if it is possible so others can also benefit out of it.
I mean, not. Through textbook I get a doubts, ma'am. Through not assignment questions. I'm appearing for final exam also, so I'm
Yeah, yeah.
practicing more problems. That's why.
No, it's okay. You can discuss over here. Anyways, today we don't have many problems, so you can stay back and discuss. Uh,
Okay, ma'am.
yeah. So, good evening, everyone. We are at week 11. And today we'll be talking about a new topic and one of the most important topics in terms of circuits. And the topic is related to stability. So there are only like four of you present. So should we wait some more time, like 3-4 minutes more, so others can join, or shall we begin?
Begin, ma'am, because we can discuss any.
Okay.
They will see what recording
Sure.
session.
So let's begin with today's session. So the topic for today's session is stability. So what is your understanding about stability? What do you understand by stability? First of all, let's answer that question. What is stability?
Ma'am, it should be. Output should be in control with the input, ma'am.
Okay. Yeah, output should be in control with input. So stability in general also means something under control. Correct? In layman's term also, stability means something under control. So when we talk about circuit stability, we are talking about output that is under control. So in very technical terms, how stability is explained is for an for a bounded input, if you obtain a bounded output, then the circuit is stable. So this is what is known as stability. Like if you have a bounded input and you get a bounded output, then your circuit is considered to be stable. Now the question is, what is bounded input, right? What is bounded input? Have you ever heard about it?
Yes, ma'am.
What is it?
Ma'am, in signal system point of view, it should be a finite value, ma'am.
Yes. So bounded means it has certain limit, right? So basically, it is a single value or it is controlled, like it is a controlled input. So let's say you have a step input. From signals and systems point of view only, let's say you have a step input. So step input has a value A, and this value remains constant throughout, right? It is not increasing, not reducing. So it is a bounded input. Now, when we say a bounded output, that means your output should also be bounded, like it should be in a certain limit. Okay. Now, when we observe, like for this type of input, what are the possible outputs that you can obtain is something which leads to your different types of stabilities and corresponding circuits, right? So when you have this type of step input, the first case for your output can be, okay, let's say, So for this input, let's say it is a unit step input, okay? So this input, you can have first output, let's say somewhat like this. So what is happening? Your output is slowly rising with input, and at the end it settles with your input. It slowly rises and ultimately settles down with your input. This is your output and this is your input. So now, is your output bounded in this particular case? What would you say?
No, ma'am. No, ma'am.
Is it not a bounded? Why? Why is it not bounded?
Because it is a tends to infinity, na?
Where it is tending to infinity?
Means it is starting at a finite value. There is no limit, na?
No.
Go ahead.
See, when we are talking about bounded input or output,
It is
majorly.
starting certain value.
No. So majorly we are talking about like your amplitude, correct? So here, if you observe your amplitude for your input was 1, which was a constant value, correct? Now what is happening? Your output is also increasing and trying to reach that single value of 1, right? So it
Yes,
is
ma'am.
not
It means
like
there is
your,
a transient.
yeah.
Yeah,
So
under
it
a
is,
transient condition.
yes, it is in transient condition, but you see in a steady state. So it is a stable situation, right? At the end, it will stabilize and it will reach your output value or a constant value, correct?
Yes, ma'am.
So this is a bounded output, bounded input, bounded output condition, which means your circuit is stable. When you see this type of response, that means your circuit is stable. Okay. Now let's go for second type of output. The second case that you can obtain is like you're providing your like you have provided your input, but what is happening is your output is sort of oscillating around your input, and ultimately it is a damped oscillation. That means your oscillation amplitude is reducing. So if we look at a steady state condition again, what will happen? Your output is again stabilizing, right? It will attain a single value and it will become stable. So here also your system is bounded input, bounded output system, which means your system is again stable. Okay. Now moving to your third case. So similar to the second case, let's say you have again applied the same input, but your output is like it was rising, then it started oscillating around your input. But unfortunately, what happened? Your oscillations were sustained. That means your amplitude of oscillation remains constant throughout. Now, what type of situation is this? So your output, and when we say that system is completely stable, is like for a unit step, you are getting like a constant value, no? But here you are not getting a constant value. Like if you expand the scale to infinity, your time scale to infinity, still you'll observe the oscillations, and they will have like sustained oscillation, which means your amplitude remains constant. So in this case, your system is not stable, rather it is marginally stable. That means you can still predict your output in a certain range at your like steady state or infinity, because it will not go beyond this bound. Your output will not go beyond this bound. So this type of system is known as marginally stable system. Marginally stable system. This is a third type of output that you can obtain. And the final fourth type of output that you can obtain is like similarly it will rise in the beginning. Then what will happen? Again it is oscillating, but slowly the amplitude of oscillation starts to increase. So now what will happen in the infinity? Is if the time scale is extended to infinity, what will you observe at the infinity?
Overdamped, ma'am.
So it is like your amplitude will start rising, and at the infinity, you can say your output will tend to infinity. The span of your output will tend to infinity. So this type of observation is obtained from an unstable system. Unstable system. So these are the basic four types of systems that you can obtain. Like you can get from like these type of outputs you can get from your circuits. So this first one is stable system. We also call it overdamped system. The second one is a damped system. Third one is marginally stable system, or you can say like it is a sustained oscillation system, but most commonly the terminology used for this type of behavior is marginally stable system. And like this is unstable, so we don't name it like anything. But people do call it like underdamped system and all, but majorly it is a unstable system. Now, you know that okay, these type of outputs you can see, but what type of transfer functions or which type of circuits will give you this these behaviors is something which we need to keep in mind. So for analyzing your transfer functions, we always write our transfer functions in j omega format or s format, right? We always find our transfer functions in terms of s or j omega, correct? So whenever we are talking about stability, we work on that same S plane.
In
And
frequency domain, we will work, ma'am.
yeah, we work in the frequency domain, and the plane that we use to define our poles and zeros. And see, ultimately, when we say your circuit gives a certain behavior, what is the reason behind that behavior? It is the placement of poles and zeros, correct? How your poles and zeros are placed and how your poles and zeros are appearing in a certain domain, majorly which is a frequency domain, that will decide your circuit behavior. So the plane that we use to analyze this pole zero behavior is known as S plane. This S plane has two axes. The real axis is called sigma axis, plus minus sigma. This is the real axis. And this is j omega axis, which is an imaginary axis. So while finding your transfer functions and finding your poles and zeros, you might have come across there are poles and zeros which sometimes appear in like completely real format, but sometimes they are in complex format, right? So you will place your poles and zeros in this particular plane, and this will basically decide what is the behavior of your system. So that's how you define whether your system is stable or not. So first of all, like this is your simple left hand side. Sorry, this is right hand side of your plane. RHS of your plane. This is LHS of your plane. So let's take a two-pole system. Okay. For two-pole system, P1 and P2. How can we place our poles? So we can have our poles over here, which are like completely imaginary poles. Poles on the left hand side, which has like both real as well as imaginary part. And the extreme cases, both the poles are at same position, which means both the poles are real. Correct? These are the three conditions possible for a two-pole system. Similarly, on your right hand side also, you can have this type of arrangement, right? Same thing. But one thing to be kept in mind, that right hand side poles will lead to an unstable system. Always right hand side poles will lead to unstable system. So these all will lead to unstable system. We'll talk about it, like how it comes to be unstable system. But right hand side pole will always be a unstable system. Right hand side poles means when you are writing like your S minus, like S minus P1, let's say A S minus P1, S minus P2 is your transfer function. Then what are the poles? S equal to P1, S equal to P2. So that means positive P, right? Positive means on the right hand side. So these lead to unstable systems. Now, when we have left hand side poles, so the poles which are only imaginary in nature, these will give you a marginally stable system. The poles on y-axis or only imaginary part will give you a marginally stable system. Now these poles, which are both like which are both real as well as imaginary part, these will give you a moderately stable system. And the final one with the real poles will give you, so these are real poles. These are like sigma plus minus j omega, and these are only plus minus j omega. So these real poles are like, they will give you the stable system. So if we observe from these three, so this damped system we can obtain from a real poles based system. These overdamped one can be obtained from real pole system. Damped system can be obtained by sigma plus minus j omega. That is moderately stable. Like it is stable, but compared to this is less stable. And this marginally stable system will have poles in form of sigma j omega, which is only imaginary part. and these have RHS poles. Okay. So this is how the poles in zero distribution looks like. So the basic idea is why we are saying that, okay, this is how it will look like. So let's dive into that. So how does your poles in zero appear into picture? So you always have a system with a feedback, correct? Now there are two types of feedbacks that are possible, right? So this is, let's say, your A input, output. So you have two types of system available. First thing is, let's say you are feeding back your output to your input with a negation. And second thing, what you can do, you can add your output to your input in this fashion. So here what is happening at this particular point, your input was there, that is V in. So here for this circuit with gain A, the input that you are getting is V in minus beta times of V out. This is being fed to your A. And at this point, what is the output that you will be getting? It is A times of V in minus beta times of V out. Correct? Now this is what you are feeding into beta. So again, beta will get multiplied. So this is A beta, V in minus beta V out. And this is again getting subtracted. So here earlier it was like V in minus beta V out. Now it is minus A beta times V in minus beta V out. Correct? And this is continuously looping. So it is a continuous loop. So what you will observe is that your input, effective input, I should say, effective input is always reducing. Correct? Now, since effective input is always reducing and your output is gain times of effective input, correct? So this leads to reduction in effective output also. Correct. Your effective input is reducing every time because of this negative feedback. We call this as negative feedback. Because you are subtracting your output with a factor from your input. So this is a negative feedback. So in case of your negative feedback, what is happening is the effective input is always reducing, leading to reduction in your effective output. So at the end, what will happen? The output will always stay bounded or limited. Correct? Because if it wants to, like, if it tries to increase the output, then also it cannot increase because you have this negative input, like negative feedback, which ultimately will lead to reduction in your output, and in a sense it stabilizes your system. Okay, so this leads to stabilizing the system. So this is how your negative feedback works. Correct? Now let's see how your positive feedback will work. So positive feedback is just opposite to your negative feedback, right? So what will happen? In case of positive feedback, let's say you are starting with V in. At this particular point, you will have A times of V in, or like let's say you have already got some output here already. There was V out at the beginning, so you have beta times of V out. So at this particular point, it is V in plus beta V out. This gets multiplied by A after passing through. So this A is basically an amplifier. You can think of it like that. It is an amplifier. So it is A times of V in plus beta V out. This gets multiplied by this beta, and here you will get A beta V in plus beta V out. Right? Now for second cycle, V in effective is V in plus A beta V in plus beta V out, and V out effective is A times V in plus A beta into V in plus beta V out. This is again being fed to input. So for third cycle, V in effective will be V in Hello.
Yes, ma'am.
Yeah, I was audible, right? I guess I got disconnected.
Yes, ma'am. Now it's fine.
Now it is fine, no? So yeah, so that is what I was saying. See, if you have your positive feedback, so what is happening after every cycle, you are basically increasing your effective input by a certain amount, hence leading to increase in your effective output. So what is happening is, as time passes on, your output starts rising, and it will give you a behavior somewhat like this, so leading to an unstable system. Correct? So this will lead to instability. So this is an unstable system. So if we want to see, okay, from so this is the basic thing that you can, like basic idea you can get simply after looking at this circuit, right? Now what happens if we talk about the transfer functions, like from transfer function point of view? So what happens is, yeah. So for a negative feedback, you have your V in and V out. How would you write your closed loop gain? Is closed loop gain is written as A upon 1 plus A beta. So if you observe, actually the gain has reduced, right? Earlier open loop gain was A. Now it has become A upon 1 plus A into beta, which is a number bigger than A, right? Now similarly, when you have a positive feedback, the closed loop gain becomes A upon 1 minus A times of beta. Here also the open loop gain of your amplifier was A. So for worst case is when your beta is 1, that means you are feeding all of your output to the input. So at that case, your closed loop gain becomes A upon 1 plus A, which is definitely greater than, less than A, right? And here for beta equal to 1, the closed loop gain will become A upon 1 minus A, which is less than A. So, no, so this is greater than A. Yeah. 1 minus A, right? So you are subtracting something from A and you are dividing it. So it will ultimately increase your gain. So this is the reason that you get the stability, because you are effectively reducing the gain of your system. So what happens is because of this behavior, your output stays bounded. But here you are continuously, like here you are trying to increase your gain. So already your gain was, let's say, very high. For say you have an op-amp, right? Your op-amp open loop gain is very high. Like it is 10 to the power 5 to 10 to the power 6 open loop gain in general for an op-amp. Now, if you're using it in a positive feedback loop, so you'll again increase the gain further. So let's say you have got a gain of 10 to the power 10. But how does an op-amp work? So if you have an op-amp, right, it has two inputs, V1 and V2. It has, let's say, a single input op-amp. The maximum output that you can get should be in range from VDD to ground, VDD to VSS, right? Now, if your gain earlier, A naught, which is open loop gain, was 10 to the power 5 volts by volts, and your VDD is say 10 volts, right? So how small your signal, input signal should be so that your output will give you a linear scaling rather than saturating your output. Can you imagine? Like what you can get is from this particular circuit, your output can maximum go, output max can be 10 volts. You cannot go beyond that. The moment you go beyond that, your output will saturate at 10 volts. But you want to see a linear progression, right? Like if you are giving an input, you want to see an output from your op-amp rather than a straight line, which is at 10 volts. So for a 10 to the power 5 volts of gain, you know that yes. So you know that V out is A naught into V1 minus V2, and this can maximum go till 10 volts, and your gain is 10 to the power 5. Delta V in is 10 volts. So delta V in should be 10 to the power minus 4 volts. So your V in should be in the range of 1/10 of millivolts. Correct? And this is the maximum that you can give. Like this is the maximum value because here it was maximum. So your input should always be less than this to see the behavior of your amplification through an op-amp. Now what is happening? You are providing a positive feedback. So as we observed over here, what it does, positive feedback basically increases your gain further. So let's say now with positive feedback, your closed loop gain becomes 10 to the power 7. It has increased your gain by 100 times. Now, what is the limit of your input? So it is 10 to the power 7 into delta V in max. Should be again output will remain to 10 volt maximum. So which will lead to your V in max being 10 to the power minus 6 volts, which is the maximum input that you can apply to your circuit becomes in microvolts. If you go beyond 1 microvolt, your circuit will saturate. You will not see any operation out of your op-amp. Can you see the importance of your feedbacks? Now, if let's say you have a negative feedback, and we know that negative feedback reduces your gain. So the closed loop gain now, let's say, has become 10 to the power 3. So what is the maximum output that you can, maximum input difference that you can provide is 10 to the power minus 2 volts. That means 10 millivolts. So can you see how your feedback is actually providing you the leniency in terms of uh, input range? Like here you can give, so this is the maximum input range, right? Like let's say your minimum input can be 1 nanovolt. Okay. For example, if your minimum input is 1 nanovolt, so in case of negative feedback, you have a range from 10 to the power minus 9 to 10 to the power minus 2. This is input range. In case of your positive feedback, the input range is 10 to the power minus 9 to 10 to the power minus 6. Whereas in case of your normal op-amp, that is open loop one, it is 10 to the power minus 9 to 10 to the power minus 4. So can you see how we have increased our input range, that is the amount of inputs that we can provide, so that we can use our circuits reasonably well. So we have increased the input range with negative feedbacks. And ideally, the gains which are used for your op-amps in negative feedbacks are way less. Like here, we are considering a gain of 1000, but generally we use, we design the op-amps for 50, 100 feedback loop, like in feedback also. So it basically increases your input range. So that's where you use your feedbacks. Now, okay, so this is what we know about feedbacks. Now coming back again to two-pole system. Two-pole system is a very important type of system because majority of the times the system that you get or the circuit that you obtain is most of the times a two-pole system. And okay, so let's say when your instability starts to come into picture, right? So how do we define instability in theoretical terms? Is through a term called phase margin. Okay, so here what we do is there is a transfer function, right? H of s. What we will do, we'll calculate the phase of this system. Phase of the transfer function is calculated. Now, when your gain is 1 or 0 dBs, 1 volt by 1 or 0 dBs, this is mod of H. When your gain is 1 volt by volt or 0 dBs, at that point, what is the phase? Phase at 0 dB is calculated, and that particular phase is subtracted from 180 degrees. So phase margin is 180 degrees minus, let's say, mod of, which is 0 degrees. So how much of phase is left from 180 degrees at this particular value of 1 volt by volt? Okay, this is how we define the phase margin. So for very basic information, the phase introduced by one pole, maximum phase, okay, so maximum phase introduced by one pole is minus 90 degrees, and 10 is plus 90 degrees. Okay, now if you have a single pole system, for one pole system, okay, for one pole system, since there is one single pole, I have to rejoin. Just wait, I'll rejoin again. Yeah. For a one pole system, there is only one pole. So max phase that it can introduce is 90 degrees minus 90 degrees, right? So if I write the phase margin at any gain, it will be always 180 minus mod of 90, right? Minus 90. So I'm always left with a phase margin of 90 degrees. That means your phase margin should never go to 0. If phase margin is 0, phase margin equal to 0, then unstable system. So that is the idea. If phase margin is 0, that means your system is unstable. But in case of your one pole system, your phase margin will remain 90 degrees. At max, like minimum phase that you can get from a single pole system is 90 degrees. So your system is always stable. So single pole system is always stable. Now when we talk about two pole system, for two pole system, now there can be a situation that let's say if I'm drawing an S plane and there are two poles. So this is like in terms of, I should not say S-plane, rather I'd say, let's say it is a Bode plot, okay? There is a slight difference in Bode plot and S-plane. So in S-plane, we talk about a complete frequency domain plane with real part and imaginary part. But when it is a Bode plot, it is rather a frequency response with gain, and where these frequencies, basically here frequencies are ultimately your poles and zeros, right? How you write your poles and zeros, S equal to something, and this S is a frequency. So it is basically a plot which shows your poles and zeros and how your gain changes with poles and zeros. So that is the idea of your Bode plot. So in this Bode plot, let's say you have a two-pole system. One pole is here, another pole is far away. Okay, very far away. Then the chances are that this pole can give you minus 90 degrees and this pole can give you a phase of minus 90 degrees, such that they are not interfering with each other. So the phase margin can be given as 180 minus 2 times of 90. Minus 90, correct? And this is in mod. So which is 0 degrees. So there is a chance in two-pole system that you can have a phase margin of 0 degrees. Correct? You can have a phase margin of 0 degrees when two poles are very far apart. And this will lead to instability. So that's why we start analyzing two-pole systems. But in practical scenario, never a pole can give you complete 90 degrees when there are two-pole systems. So 90 degrees means there is no interaction with the second pole. So you can imagine like how far your second pole should be such that there is no interaction. So two-pole systems are most of the time stable. There might be some chances that they are not stable, but otherwise they can be stable. So this is the worst case, right? So this is the worst case when these two poles can give you an actual phase shift of 180 degrees. So this is the worst case. Now beyond this, if you go for a three-pole system, then in three-pole system, definitely you can get an instability point. Because let's say if they are not providing you the fullest of their phase difference, that is the fullest of phase contribution of 90 degrees, still since there are three poles, they can contribute to 180 degree phase shift and you can get an unstable system. So the two pole system is somewhere in the margin between an unstable system and a stable system, whereas one pole system, single pole system is always stable, and three pole system can majorly be unstable, or you place your poles such that your system can be stable. So that's why people start analyzing two pole systems, and two pole systems are important. And also majority of the times the systems that you observe are two pole systems. So that's why two pole systems are analyzed. Now talking about two-pole system, so let's say you have a two-pole system such that its open loop gain is ADC upon S. Okay, so 1 upon S omega P1, 1 plus S upon omega P2. So this is one way of representing the two-pole system, where your loop gain A naught at S equal to 0, which is DC gain, will give you exact ADC. Now, for suppose if you write A naught as ADC upon S plus omega P1, S plus omega P2. So here you know that, okay, your DC gain is exactly equal to ADC. But in this particular case, your DC open loop gain is not actually ADC, rather it is ADC upon omega P1 into omega P2. So both the representations are correct, just that you have to keep in mind, okay, what is the DC gain that you are getting? Why I'm focusing on DC gains? Because ultimately when you have a system, you will draw its Bode plot, right? That Bode plot only will give you the information about phase margin and everything. And for that Bode plot, you'll start from your DC gain. And that's why that DC gain is very important. So you can represent your transfer function in either ways, but keep these things in mind. Now here you cannot write your DC gain directly as ADC, because as you put your S to 0, the gain that you are getting is not ADC, rather it is ADC upon omega P1 into omega P2. So that is the idea. Now, since this is an open loop gain, so for closed loop gain, in the worst case scenario, it will be A naught upon 1 plus A naught. So which is ADC omega P1 omega P2 upon S square plus omega P1 omega P2 S plus omega P1 omega P2 ADC plus 1. So now we know that ADC is much greater than 1. So we can write ADC plus 1 as almost equal to ADC. So the closed loop gain that we get finally is ADC omega P1 omega P2 upon S square plus omega P1 plus omega P2 of S plus omega P1 omega P2 ADC. So this is the final transfer function that we get. And very common way of representing your transfer function is common two-pole system transfer function representation. Common two-pole system transfer function representation is like h of s is omega n square, where omega n is constant, okay? Omega n square, s square plus 2 alpha omega n s plus omega n square. Now from here, if you try to observe these two are actually equivalent, correct? And from here you know that, okay, omega n is root under ADC omega P1 omega P2, and this 2 alpha is 2 alpha omega n is omega P1 plus omega P2, which makes your 2 alpha as omega P1 plus omega P2 upon root over ADC omega P1 omega P2. So this is the values that you get for omega n and 2 alpha. So this particular 2 alpha is known as damping factor. Why damping factor? Because first of all, this was a negative feedback system, right? So in negative feedback, you will ideally have damping for stability. And how much damping will be there in your circuit is defined by this particular factor, which is known as the damping factor given by 2 alpha. Now, there can be cases. So case 1 is when your omega P1 is equal to omega P2 equal to omega P. That is, both your both your poles are at the same point. They have the same values at that particular point or same frequencies. Your omega n will become root over ADC into omega P, and your alpha 2 alpha will become 2 omega P upon root ADC into omega P, that is 2 root ADC. So alpha is 1 upon root under ADC, right? Now we know ADC is very high, so very high than 1, so which will give like alpha almost equal to 0. So if alpha is almost equal to 0 in this particular case, when your ADC is very high, how your transfer function will look like? Your transfer function will become omega n square upon s square plus omega n square, right? So if we see, okay, what are the values of poles? We will have two poles, s square plus omega square, right? So poles will be s square plus omega n square equal to 0. So s square is minus omega n square. So s square, s is plus minus omega n I or j. So these are two imaginary poles.
Marginally stable, no, ma'am.
So
Will lie
marginally
on.
stable. Yes. So the system is marginally stable as we observed earlier. So for a step input like this, so this is your input. For this step input, your output will look like this as we discussed earlier, and it will constantly oscillate. So this will give rise to a marginally stable system. Now, the second case is now this was case 1. So case 2 is omega p2 much greater than omega p1. Now ideally let's take like omega p2 is 4 times of omega p1 just for a value. So what will happen? How do we write our alpha? It is omega p1 plus omega p2 upon root under ADC omega p1 omega p2. So which will be omega p1 plus 4 times of omega p1 upon root under ADC into omega p1 into 4 times of omega p1. So giving rise to 5 upon 2 root ADC. Correct? So this is the exact value that we are getting for alpha. Now we can also write alpha as okay. So can I write my alpha as omega p1 omega p2 whole square root under by root under ADC omega p1 omega p2? I can write it like this, right? So it's just rewriting it again to do further some simplifications. So it is simply 1 by root ADC. I can get it out. Then I'll be left with omega p1 square plus omega p2 square plus 2 omega p1 p2 whole divided by omega p1 omega p2 of whole root. So this will give us 1 upon root over ADC omega p1 by omega p2 plus omega p2 by omega p1 plus 2 1 by 2. Now here we know that omega p2 is 4 omega p1. So it will be root under ADC omega p1 by 4 omega p1 plus omega t1 into 4 by omega p1 plus 2, 1 by 2. So this cancel, this cancel.
$6.25, ma'am.
Yes, alpha is 1 by root ADC, 1 upon 4 plus 4 plus 2, 1 upon 2. So here, if we write like what we took. Achha, we took omega p2 is 4 times of omega p1, right? So rather than this, let's take it like a very large value. So this is only 4 times, no? So it is not that large. So let's make it even larger value. How can we make it even larger? So we can make it even larger. So this was one analysis that we already did, right? So for very large value, I am making it like rather than this 4 times, I'm also including ADC also. So I'm including like DC gain times 4 into pole value. So it is a very large separation, huge separation. So in that particular case, what will happen? Plus 2 root under. So here you will have ADC, here you will have ADC plus 2 and half. Now you know ADC is much greater than 1. So which will make it like root under ADC. This tends to 0. And ADC, 4 times of ADC plus 2 will ultimately give you 4 ADC. 4 ADC square root under. So alpha will become
Ma'am.
something is missing here. So this was 2 alpha, right? This was 2 alpha, yes. These all values are 2 alpha. This is also 2 alpha is omega p1 plus p2. So this 2 will also come here. So into 2. So that this was 4 by 5 root under ADC for this. This is 2 alpha. So here you will have a factor of 2, 2, 2, 2. And here we are getting 2 root ADC by 2 root ADC, which ultimately gives your alpha as 1. So alpha is almost equal to 1. This is the case when your omega p2 is almost equal to 4 times of ADC into omega p1, like huge separation, very huge separation. So in that particular case, your alpha that you are getting is 1. So means 2 alpha will be 2. So yes. So here, since your alpha is 1, how your this will look like transfer function, which is will be omega n square upon s square plus 2 alpha omega n s, right? Alpha is 1. So 2 omega n s plus omega n square. So this is omega n square by s plus omega n whole square. Correct? So now here your omega n, s is equal to minus omega n. So there are 2 poles and both are real poles. So how does the system look like when you have 2 poles and both the systems are both the poles are real? So there are 2 poles and both the poles are real. So the circuit or the response that you will get is like if this is an input, so you will get overdamped system. That means you will get this type of response. This is output and your system is completely stable. So when your alpha is 1, your system is stable. When your alpha was alpha was almost 0, your system was marginally stable. And when your alpha, now case 3 can be alpha greater than 1, right? So which was not this case. So the case when alpha is greater than 1, what will happen is you will get a damped system, which is stable, but it is not like over damped system. Rather, it is a simply damped system. So it is input, then your output will look like this. So this is your output, and this is also stable. So based on your alpha values from your transfer function, especially for a second order transfer function or two pole system, based on the values of alpha that you get, you can predict your stability from this system for these systems. Now, as I was saying, phase margin. So Bode plot, are you all aware of Bode plots? Or do you want me to explain like what are Bode plots? Maybe I'll quickly go through them because Bode plots are very important when we are talking about analog circuits. So let's quickly see what are Bode plots. So Bode plots, there are two parts in a Bode plot. Okay, first, so Bode plot has a magnitude plot and a phase plot. So it is magnitude versus frequency, and this is phase versus frequency. Okay, so you will have two plots. You know that you have a transfer function which is h of s. Now for this you will find mod h of s, which is magnitude, and angle h of s, which is phase, and these will be in terms of s or omega, correct? Here also you will get it in terms of s or omega. These are frequency dependent. So what you do, you plot them with respect to frequency. This is, let's say, magnitude plot. This is your angle phase plot. So you will have some gain, like let's say you have certain DC gain, then you encounter first pole. So pole will basically introduce a 20 dB, negative 20 dB per decade of slope. Whereas when you encounter, let's say, a 0, so you will observe a positive 20 dB per decade slope. But here it was a negative plus, so 20 dB negative slope and plus 20 dB positive slope. So it nullifies both of them, and ultimately you are getting a 0 slope, right? Similarly, again, let's say if you get another 0 at this particular point, so you will have a plus 20 dB per decade slope. If you see like two poles, so you will have a 40 dB per decade slope. So 20 nullifies over here, another 20. So you will see 20 dB per decade resultant slope corresponding to these two poles. So this is how you draw your Bode plot. So whatever you will get your poles, so these are all poles and zeros. So whatever the poles and zero values that you get, you will place them according to their frequencies, and you will see how many poles are there, how many zeros are there. Each pole corresponds to minus 20 dB per decade slope, and each zero corresponds to plus 20 dB per decade slope. Now, corresponding to this h of s, you will have a certain angle, right? And that angle also changes with your like with your frequencies. So let's say your you started with 0 degrees of phase. At DC point, your phase was 0, and you are slowly decreasing your phase. And this is, let's say, 180 degrees or minus 180 degrees. And that's how your phase looks like. So the idea was, when I said phase margin, the idea is that this is 0 dBs, right? So when we are talking about phase margin, let's say your H of S is somewhat like this, and this is like two pole system. So minus 40 dB per decade. Here, let's say the gain was 40 dBs. You encountered your poles at 100 hertz. So what will be the frequency over here when you're, and what is the gain over here? So this is 0 dB that you know, because the excess we call it as 0 dB. This is 40 dB per decade slope. Decade means 10 times. So per decade slope of minus 40 dB, your gain, DC gain was 40 dB. So what is this frequency? And this is phase. Yes. So what will be this frequency if it was 100 hertz over here?
Sorry, ma'am, could you please repeat again, ma'am?
Sorry. So yeah, I said that you have a 40 dB DC gain. This is known as DC gain also. Okay,
Yes,
straight
ma'am.
line DC gain. You have a 40 dB DC gain. At 100 hertz, you encounter two poles. Okay. So with two poles, corresponding to two poles, you know that your slope will be minus 40 dB per decade, like minus 20 dB per decade per pole. So for two poles, it is minus 40 dB per decade, right? So
Yes,
at
ma'am.
certain frequency, it will cross your 0 dB point. Now my
Yes,
question
ma'am.
is, what is this frequency where it crosses 0 dB?
Unity bandwidth, ma'am. Sorry,
Yes,
unity frequency.
unity frequency, unity gain frequency. So what is this particular frequency?
Ma'am, it is okay. Okay. Yeah, we need to find out, ma'am, that thing. That is that would be DC gain divided by the poles, I think.
No, so it's
Quantum.
not that complicated or that difficult. See, you have 40 dBs, right? Your slope is 40 dB minus 40 dB per decade. For a decade, your slope will change by 40 dBs. Basically, it will reduce by 40 dBs. So if you already had a 40 dB gain, so after one decade, your gain will be 40 minus 40, which is 0 dBs. Correct?
Yes, ma'am.
And this is the 0 dB that I'm talking about. So how much will be after one decade? So one decade, if it is 100 hertz, then here it will be 1000 hertz.
1 kilo. Yes,
Correct?
ma'am.
Because decade means 10 times.
Yes, ma'am.
Decade is 10 times. So at 1000 hertz, your system will have 0 dB gain. Okay? And after that, your system will behave as an attenuator rather than as an amplifier. So that is the idea. When it has like constant gain, so that means in this particular frequency range till 100 hertz, your system will give you like if you introduce your or if you input your system, basically this is an amplifier. Okay. So in this particular amplifier, if your input frequency range is from 0 hertz to 100 hertz, your amplifier will give a range of like if it will give an amplification of 40 dBs. Okay. After 100 hertz, what will happen? it will start reducing your gain because of this slope. That is what you understand. So your gain starts reducing after 100 hertz. And after 1000, at exact 1000 hertz, what will happen? 0 dB gain. That means unity gain. Unity gain means whatever is the amplitude of your input, your output will have the same amplitude. So there is no amplification at all. Now, beyond that frequency, what will happen? Your gain is negative. Negative means less than 1. And what does a less than 1 gain mean? Basically, it is an attenuator. If you are providing a signal of 10 like 10 volts amplitude, and you are getting a signal of 5 volts amplitude out of a system, that means it is attenuating your signal. So beyond this point, your system will behave as an attenuator beyond this unity gain point. Clear? So this is the information that you get from
That
your
100 hertz is the 3 dB frequency, na?
100 hertz, yes, 3 dB frequency. So here what is happening, the plot that I have drawn is an approximate Bode plot. We call it as an approximate Bode plot. But if you go for an exact Bode plot, what happens is, like, if you have one pole, so at that pole your DC gain drops by 3 dBs. Now here, since it is it has two poles, both the poles at the same point, the gain will drop by 6 dBs. So it is per pole, slope will be 20 times of n. Okay, like for poles, if I say 20 times of n dB per decade, so this is how the slope changes. And if I say gain, it will be minus 3 into n dBs. So number of poles utna into 3. So here, since it had two poles, so if I'll draw an exact Bode plot, how the exact Bode plot will look like. So this is an approximate Bode plot. Bode plot. The exact Bode plot will look like this. So it will start from it will start from somewhere here. It will merge with this one. Ultimately, it will follow this path. But at this point, what you will observe is your gain at this frequency, that pole frequency, your gain will actually be 34 dBs. That is minus 6. So this change is of 6 dBs. This is 6 dBs. The difference. So this one is exact Bode plot. Okay, so this is exact Bode plot. This is approximate Bode plot. And corresponding to that, you will have phase. So you will draw the phase of your system. So let's say you started with the zero phase, and two poles. Since you have two poles over here, the exact phase that it will introduce is minus 90 degrees. So here you will reach like minus 90 degrees, and here the phase is further reducing. So the idea is, at this particular unity gain frequency, what is the phase? Okay, and phase margin is given by 180 degrees minus mod of phase. Or if you want to use the exact values, you can write like minus 180 minus the phase, because the phase will be generally in negative. So whatever the phase is, that will be like subtracted from 180. And if phase margin is 0, then system is unstable. Phase margin should be always greater than 0. Like in this particular case, not to be confused, let's write it down for this mod situation. So here, if phase margin equal to 0, system is unstable. Phase margin greater than 0, it is stable. So that's how, based on your phase margin, you define whether your system is stable or unstable. So the very first thing, the moment you see a circuit, any analog circuit or any basic circuit, and you have to analyze that system, the first thing that you do, rather to find out its functionality, its stability, anything, the first thing that you will do is find its transfer function. After that, you find the Bode plot. You draw the Bode plot. And also you saw, okay, how we are finding the stability. Now, how do we find the functionality of the circuit? So that is also done through this Bode plot itself. So let's say you know that this can be understood, stability can be understood by Bode plot. Now, other uses, if I say, okay, uses of Bode plot. First use is stability understanding. The first use of Bode plot is stability understanding. And second use, which is like the major use of Bode plot, is the major use of Bode plot is I don't know whether it's coming or not. Anyways, major use of Bode plot is functionality determination, to determine the functionality of your circuit. Now, for example, let's say you have a circuit, okay, and its Bode plot is given. Majority of the times, let's say the phase, magnitude Bode plot is given, okay. So there is a circuit with this type of Bode plot. So what does this mean? It passes lower frequencies. Your circuit passes your lower frequencies, and higher frequencies are being attenuated by the circuit. So what type of functionality that this circuit have? A circuit which can pass low frequencies and block the higher frequencies. So basically it is a low pass filter. Have you heard of filters? In general, filters, low pass, high pass, band stop. So filter basically means it is a circuit which will allow a certain amount of frequencies to pass through it, and remaining frequencies are attenuated. Okay. Now, if this is a low pass filter, how about this? What type of filter is this?
High pass filter.
So it is a high pass filter, yes. So this is an HPF. We call it HPF or high pass filter. Now, if you have behavior somewhat like this, what does this mean?
Band stop filter.
It is a band stop filter, correct. Band stop filter. And opposite to that, if you have this, then it is a band pass filter. Okay. So this is a band stop filter because it stops certain frequencies. Opposite to that is a band pass filter. This is a low pass filter, high pass filter. So if any circuit is given, the first thing that you do is calculate the transfer function. The second thing that you should do is find the poles and zeros, and using those poles and zeros, you draw your Bode plot. Okay, and after the Bode plot is drawn, then you analyze from the Bode plot what is the functionality of that particular circuit. Okay, let's say there is another circuit. Okay.
Ma'am, sorry for interrupting, ma'am.
Yes.
Ma'am, previously you tell me about the shortcut for unity gain frequency find out through decade. No, if zero is present in between, here it is a minus 40 dB. Now what you
Uh,
say? If it
no,
is if
no. I could not get your question. Can you repeat again? Come again.
ma'am, previously you discussed about the way to find out the unity gain frequency from the 3 dB frequency through the help of minus 40 dB per decade.
Yes, yes. It was a basic, simple example. Yes.
Yes, yes, okay, ma'am. In the same question, if zeros are present and one more
Yes.
pole are present,
Uh-huh.
how can I proceed, ma'am?
So then it won't be that easy, okay? But it can be done. And basically, if your poles and zeros are decades different, like they are placed one decade apart, two to three decade apart, it is very easy to analyze because your slope is dB per decade. But if your poles and zeros are in between, so you have to calculate your exact values. But if they are decades apart, then it is very easy to analyze. I'll give you some example. Just after this explanation, maybe we can do these type of easy things, like easy problems where you can exactly find out, okay, what is your like 0 dB frequency, or at this particular frequency, what is your gain? Those type of questions we'll do, like we'll take up some problems. But that is only easily solvable if your poles and zeros are decades apart. Like they should be decades apart, but if they are in between, then you have to go for exact calculations. Okay, so we'll do some problems for
Okay.
clear understanding. Yeah. So meanwhile, I was saying, like, let's say you have a, uh transfer function which is like so these two are like phase and frequency response of your circuit. So can you say what type of functionality does this circuit perform?
Ma'am, it is ma'am, by looking at the face, it's showing a negative now. It's
Yes.
decreasing.
Okay, yeah, you can understand like it is a negative value.
Yes,
Because
here 0 dB defines as a unity gain frequency when it
yes.
is.
So basically what this circuit is doing, it is providing a constant gain of 1 dB or 1 volt or 0 dBs throughout all the frequencies. That means your amplitude of the signal is never changing, not attenuating, not amplifying. Okay. But if you look at your phase response, you observe that at each and every frequency, your phase is changing. What does a phase change mean? Like if we see it from a time domain perspective, how does it look like? So let's say if you have a sine wave, right? So this is your sine wave of Vn. Now what is happening? You have a 90-degree phase shift at certain frequency, but your gain remains the same. That means your amplitude remains the same. So what will happen? Your sine waves will start from here correct? So if you see, it is 90-degree phase shift, right? There is a 90-degree phase shift between your input and output, but there is no change in the amplitudes. Your gain is 1. Can you see that? So this particular observation or this particular type of behavior is shown by a filter known as all-pass filter. Okay. So this is an all-pass filter, which basically means that it will pass all the frequencies without any attenuation or amplification, but it will introduce phase shift in your signals based on its frequency. So it will introduce different delays in your signals based on its frequency, but it does not change your amplitude or it does not change your amplitude. So this type of circuit is known as all pass filter. Okay. So basically, when we talk about filters, so there are basic 4 types of filters like low pass, high pass, band stop, and another filter which is used for phase shifting is known as an all pass filter. Clear? So this is an all pass filter. Now, as we were talking, let's do a very simple example. Okay. Now, let's say so in this particular Bode plot, what is your 0 dB frequency?
Ma'am, 0 dB frequency, it should be at okay.
So this is somewhere here, right? Yeah. What is this 0 dB frequency? X.
It would be in gigahertz.
Will it be in gigahertz? What is the value, exact value? Can you calculate? And how many poles and how many zeros are there? What are the poles? What are the zeros? Let's start with this point. At 10 hertz,
Three, ma'am. Totally, there are one. It would be 5 poles, ma'am.
and zeros?
Zeros are 2 zeros. At 10 hertz, 1 0, and at 10 kilohertz, 1 0.
1 0. Acha. And what about at 100 hertz?
At 100 hertz, 1 pole, ma'am.
1 pole.
Yeah, because it is decreasing, na. Okay, wait. No.
No, at 2 pole. 100 had 2 pole.
100 hertz, 2 poles. And what about at 100 kilohertz?
Yes, 4
It's
poles.
4 pole.
4 poles, right? Okay, so you got it correct. Like 1 pole, 1 0 at 10 hertz, because your Bode plot is increasing by 20 dB per decade slope. At 100 hertz, it was already 20 dBs. Now you are resultant seeing at minus 20 dBs. So the difference is minus 40 dBs. Minus 40 dB per decade means 2 poles. Now again at 10 kilohertz, it has gone to 0. That means one pole has minus 20 dB has been compensated by plus 20 dBs. That means 1 0. Now at 100 kilohertz, it was already at 0 dB per decade. Now it is giving minus 80 dB per decade. That means 20 into 4 will give you 80. That means 4 poles, right? So there are 4 poles at 10 kilohertz. Now the question is, okay, so what is the gain over here? What is the gain at this point? It has increased by 20 dB per decade. So what is the gain at this point?
It should be greater. I mean, 120 dB, ma'am.
Yes. Because the change is of 1 dB, that means your gain will increase by 20. So it is 120 dBs. Correct? Now, what about this point? How much is the frequency change?
40 dB. Four, 2 poles are changing, no? It is
No, but
YTD.
no. Wait. So here, 100 hertz to 10 kilohertz. How much is the frequency change? How much is the frequency change?
90 hertz, ma'am.
90 hertz?
Means from 10 hertz to 100 hertz, effective change in the frequencies.
100 hertz to 10 kilohertz. How many decades are changing?
Okay, fine. Yeah, ma'am.
So it is 1 decade from 100 to 1000. Another decade from 1000 to 10,000. So there are 2 decades of change. So 2 decades of change means your gain will reduce by how much?
40 dB, ma'am. 60.
40 dBs. So here earlier it was 120. Now it will become how much?
60 dB.
Why 60?
Oh, sorry. 40. Yeah.
20 from here.
Okay.
Another 20, right? So total 40. So it will be 80 dBs. Correct?
Yes, ma'am. Yeah, we need to. Yeah, I look at 100 dB, ma'am. Yeah, I get the point.
Yeah. No. At this particular point, see, you have to analyze from that one frequency to another you are seeing, right? So from that gain to other gain, you have to see. So now it is at 80 dBs. So here it is 0 dB per decade, so no change in gain. Now you have shifted by 1 decade. Now here you see you have a gain of minus 80 dBs per decade. And your what I am asking is 0 dB frequency. So when will you get a 0 dB frequency? When your gain reaches 0 dB. Gain reaches 0 dB means minus 80 dB per decade. So after 1 decade only, you will see a 0 dB gain, correct? So this X should be 10 times of 100 kilohertz. So this is 1 megahertz. So unity gain frequency is 1 megahertz for this particular problem. Is this clear?
Ma'am, I didn't understand the link, ma'am.
Okay. So see, here your gain was 80 dBs, right? So at this particular point, your gain is 80 dBs. Correct?
Yes, ma'am.
The slope at this particular point is minus 80 dB per decade. I should better make it very steep. Let's say here. Okay. So this will not misguide. This is X, right? The slope is minus 80 dB per decade. Minus 80 dB per decade. This is clear. Now I'm saying that at X frequency, at X, your gain is 0 dBs. Correct?
Yes, ma'am.
Now you are transiting from 80 dBs all the way to 0 dB. Correct? So the resultant gain change is how much? 80 minus 0 is 80 dBs. Right?
Yes, ma'am. Yes, ma'am.
So your gain is changing by 80 dBs. Now here, the slope of this line is also how much? Minus 80 dB per decade. Correct?
Yes, ma'am.
So when you move by 1 decade, you can already see the gain change by 80 dBs. Right?
Yes, ma'am.
So that is what you wanted, right? You wanted a change of 80 dBs and you are getting the change of 80 dBs just by 1 decade change.
Oh, yes, ma'am. Got it, ma'am.
Right? So that's how your X will become 10 times of this particular point. So that is 1 decade shift. Clear?
Yes, ma'am. First, we need to find out the gain based on gain divided by how much it is changing is 80 dB. So,
Yes.
so
Now
per
here,
point,
let's say if it was rather than being 80 dBs, now it was, let's say 160 dBs. For example, if at this particular point, rather than it being 80 dBs, it was 160 dBs. So how much should be your X?
yeah, 160 dB na means it there.
Then it would be 100 times
Yes.
instead of 10 times.
Yes, it should be 100 times rather than being 10 times. Because so you will need 2 decade shift. 1 decade will introduce you 80 dB shift. Another decade will also introduce you a 80 dB shift. Correct. Now, what about if it was like 40 dBs? Rather than it being a 80 dB shift?
Okay, then it should be it should be 100 kilohertz.
No. It cannot be 100, right? At 100, you already have your gain at 40 dB. You want it to move to 0 dB. You have a 80 dB per decade slope. So at 1 decade, like 10 times, you will get a 80 dB difference. So for 40 dB difference, how much you will need? Five times, right? If for 10 times you are getting 80 dBs difference, for 5 times you will get a 40 dB difference, no?
Yes, ma'am. Yes, ma'am. Yeah.
So it will be 5 times.
Yeah, 500 kilohertz.
Yes.
Yeah.
500 kilohertz. So for 40 dB, it would be 500 kilohertz. For 80 dB, it will be 1 megahertz. For 160 dB, it will be 10 megahertz. So this is a very simple analysis. Like looking at the Bode plot, you can quickly solve. You don't need to go for any like mathematical calculations or anything like that. This is very simple. But sometimes the questions are not so direct, and in those cases, what you need to do is you need to actually calculate the transfer functions, place your frequencies, and get the values for unity gain frequencies. When it is not this direct. Here it was direct because I was changing everything by a decade. So when everything is changing by a decade, 2 decade, 4 decade, and your slope is also in decades, so it is very easy to solve. But if I'll take some points in between and start adding poles and zeros, the solutions will not be so easy. So at that point, you have to calculate the transfer functions clearly, and then you have to find the frequency corresponding to your 0 dB gain. Clear? Is this clear to everyone? Bode plot?
Yes, ma'am.
So Bode plot, its uses, stability. Is the concept of stability clear to everyone? And when your system is stable, when your system is unstable, always you should get S in terms of negative values. Keep in mind your S should be in left side of the plane, left hand side plane. Then only your system is stable. And in Bode plot, majority of the times you draw the Bode plot for the stable systems. But here, let's say you have a pole at positive S and at the negative S also. So Bode plot does not define two frequencies, positive and negative, right? So you will place it at the same point, but the system is already unstable. So Bode plot is most of the times drawn for like negative poles, negative S-plane poles, and then you analyze its stability. Okay? So with this, we are left with very little time today. But anyways, these concepts were very important to understand. So this first question is based on the phase margin only that we discussed, right? We discussed the phase margin, correct? So here in this particular question, it is a two-stage cascade amplifier. Cascade means the output of one circuit is one part of the circuit is given to the input of the next part of the circuit. So here, if this is input, here it is output. This output is fed to again input, and you are getting the output. So that's why this is a cascade. In cascade, your input is given to the output. So, like if I'll draw in a very simple manner, this is known as cascade. And when we draw it like this, this is cascade. Okay. Maybe in next session, we'll discuss further about the advantages, disadvantages that we get from cascade and cascade. But for now, keep in mind that this type of configuration is a cascade configuration and this type of configuration is a cascade configuration. So in this particular circuit, it is a cascade amplifier as shown with GM1, GM2. Okay, GM1, GM2 are different. GM1 is 323, GM2 is 1028 microsiemens. R1 is 71.2 K, R2 is 9.7 kilo ohms. C1 is equal to 682 femtofarad. C2 is 3640 femtofarad, and C12 is 20 femtofarad. And here the design is to be compensated by a phase margin of 75 degrees. 75 degrees phase margin. What should be the ratio of two poles of the circuit? Give your answer it should be greater than 1. Okay. So first of all, where are the two major poles that we will observe? What are the AC points that we see in this particular circuit? So this is the first AC node and this is the second AC node, correct?
Yeah.
So you will get two poles corresponding to these two AC nodes. Now, if your R1 C1, that means let's say this pole is okay. This is two. This let's say this is
Out, C out.
1 2. So if your R1 and C1, like first pole is almost equal to second pole. So what did we observe? That if first pole and second pole are coinciding with each other, how your system will be? In a two-pole system, how would your system look like? If both the poles are overlapping on one another?
Marginally stable.
Marginally stable systems. So for making your system completely stable, what should be there? Your poles should be separated apart. So that means, let's say R2, C2 should be much, much greater than R1, C1. This will lead to a stable system. So now the idea is you have to find the ratio. So if I write it in terms of ratio is like R2 upon R1 C1 should be greater than 1 for stable system. So we'll find the values of like poles and then we'll take the ratios, and if the ratio is coming out to be greater than 1, then the system is stable. Majority of the times what we want is that this pole 2 should be a dominant pole. There is another reason also because of like output impedance and those things. Yeah. So this should be like, so pole 2 and pole 1, the ratio should be greater than 1. So they should be separated. Both the poles should be separated. And if we can separate the two poles very far apart, such that your unity gain frequency comes in between these two poles, so your system is basically behaving as a unity pole system, right? And unity pole system is always stable. So in that particular frequency range, your system will always behave as a stable system. So that is the idea. So let's say if you have two poles which are very close by, so what we do, we try to shift these two poles apart. And we shift these two poles apart such that we want to create a system which is equivalent to unity pole system. So what I mean is, so let's say if your Bode plot looks like this, okay? So you have one pole, you saw drop, then there was another pole which introduced a further drop, and this is where you got your unity gain frequency, right? So your two poles are already coming in between your unity gain frequency. So both the poles are coming inside your unity gain frequency. So when what I am saying is, like, let's shift your two poles such that one pole, let's say, remains here, or it is shifted a little here or there. But we are shifting this pole to here. Okay. So such that what happens, now your system will see, okay, there is a single pole. So this will introduce minus 20 dB per decade. This will again introduce minus 20 dB. So resultant is minus 40 dB per decade after this frequency. Now here there is only one pole. So it will start introducing minus 20 dB per decade as the slope. And this will meet over here. This is your unity gain frequency. So your second pole is beyond your unity gain frequency. So now, if I look at this particular region, so there is only one pole, right? So it is equivalent to a single pole system, correct? Because there is only one pole which is encountered before your unity gain frequency. But here we have two poles, right? Here we only have one pole. So we know that this system is more stable than this one, correct?
Because of phase margin is 0, right?
Yeah, so here phase margin will definitely not be 0, but very less. We want to increase the phase margin because higher the phase margin, more the stability of the system. So we always want the most stable systems so that it is not influenced by anything. So the idea is we want to create, let's say if you have a given system, this is the system which is given to you. What we want to make it, we want to make a designed system. So given system is modified and designed like this, and this is done through the concept of compensation. We call it compensation. So through compensation, what we are doing is we are shifting the two poles apart. And how do we do that? So we add more resistors or capacitors between the circuits or between two nodes such that we increase or reduce the resultant R and C, hence changing the pole values. So this concept is known as compensation. Okay. And majority of the times, how do we compensate our compensate between the poles and zeros is we actually try to introduce one zero and modify the values of zeros. So what we do, we either introduce a capacitor or we introduce a capacitor with a resistor at this particular stage. Okay. So these two things are done to compensate. So what we can do, we can introduce a zero which can overlap with a pole and cancel that pole completely. That is one idea. Second idea is we are shifting these poles and zeros and also introducing some zeros and poles to modify our transfer function. So this method is known as compensation. Clear? And with compensation, we try to stabilize our system. So now in this particular question, we were asked to design to have the circuit with a phase margin of 75 degrees. So what will be the ratio of the two poles? So it was already mentioned in the lectures, like how you come across and how you calculate these values. So you can go through the lecture and find out. I'm directly writing the formula. It is there in the lecture. So the ratio of two poles is given by a naught square minus 1 upon 1 plus a naught cos phi minus 1 plus a naught cos phi. Here a naught is gm1 gm2 into r1 r2. gm1 gm2 r1 r2 is the a naught and phi is the phase margin value. So here phi is 75 degrees. So for phi equal to 75 degrees, we will simply substitute the values of a naught and phi, and the ratio of poles, which is named as, let's say, x, that we obtain for this particular problem is 810.98. So this is the ratio of the two poles, like the separation that needs to be there between the two poles to obtain a phase margin of 75 degrees. Okay, so this formula has been discussed thoroughly in the lecture. So please go through the NPTEL lecture for this formula. Okay. Now, moving on to the next problem. So, second problem was to calculate the values. So, you can do that on your own. Now this is a second type of formula, second type of problem. So here see, the design is to be compensated for a phase margin of 75 degrees by adding an extra capacitor in shunt to 112. What I mentioned here, this is the capacitor 112, right? So let me take the snippet, copy image, screenshot. Yeah. So as I discussed, like what they want to do in this particular question, they want to compensate this circuit for a phase margin of 75 degrees by introducing an extra capacitor CC in shunt with your 112 capacitor. So what should be the value of CC? That is the question. So you are introducing another capacitor in parallel. So the effective capacitance over this region, so it is like CC parallel to C12, so which is effectively equal to CC plus C12 because of capacitance. So the capacitance at this particular node has increased. Now how this will affect your poles? So the moment your capacitance, this capacitance increases, due to Miller capacitance, what will happen? This capacitance will have an capacitance C in here
C2 here.
and also a C out here. Correct? This C in, basically C out will be similar to your CC plus C12. There won't be much of a change. But what will happen to C12? It will become gain times of CC plus C12. So the multiplication with a gain times to that of already a new capacitor which is added, it's a huge factor of change. And that capacitance will definitely introduce the difference in the two poles. Are you getting my point? How much? So here the factor, earlier it was like earlier when there was no CC, how this C12 was changed. So C in dash was A times of C12 and C out dash was C12, correct? Now because of this introduction of CC, what will happen, this C in let's say double dash will become A times of CC plus C12. So an extra factor of A times of CC is being added. This is extra, right? And here it becomes CC plus C12. So this is, let's say, the capacitor is in some femtofarads. So this is not a big change, but here this is definitely a big change, right? And because of this big change, your like capacitance at this point is changing. And what do we mean by pole? What is a pole at a particular point or at a particular node? It is 1 upon RC, right? So if you change the value of R at that point or C at that particular point, your pole value will change. So in this particular case, your capacitor is changing. It will change your pole value and it will definitely bring a separation between the two. Correct? So that's how it is compensating. Can you see, is the picture very clear to you? Is it clear like how this compensation capacitor is actually helping you out in separating the poles? Is the picture clear to everyone?
Yeah.
Clear, right? So that is the idea. Now we know that compensation capacitor will definitely separate our poles. Now the question is, how much should be the value of this capacitor such that we can get a phase margin of 75 degrees. So here it is again solved in the like for detailed solution. You can go through the lectures. It is already there in the lectures. I'm directly writing the formula for transfer function of this particular circuit. Okay. So the transfer function of this particular circuit is R2 1 plus S C1 R1 plus C12 R upon 1 plus S R1 C12 plus R2 C2 plus R1 C1 plus R2 C12 plus GM2 R1 R2 C12 plus S square C1 C2 plus C1 C12 plus C2 C12 into R12. This is the transfer function that you get. And from here, it is clearly observed that you have two poles and 1 0. Right? In this transfer function, you have two poles and 1 0. Now, if we assume that two poles are very far apart, so that means they are not interacting with each other. So I can write it as like 1s tau 1 into 1s tau 2, such that these tau 1 and tau 2 are 1 by omega 1 and 1 by omega 2. Okay. So this will be equivalent to 1 plus s tau 1 plus s square tau 1 tau 2. So your 1 by omega p1, that is tau 1, is r1 c12 plus r2 c2 plus r1 c1 plus r2 c12 plus gm2 r1 r2 c12. So what we are doing is, here this tau 1 has been equated with the factor that we are getting for S here. Okay? Now, for tau 2, what we will do is for tau 2, see here S square tau 1 tau 2 hai, right? So if I want to find tau 2, that is omega 2, I can simply write it as the factor which I have for S square, that is C1 C2 C1 C12 plus C2 C12 into R1 R2 by tau 1, correct? R1 C12 plus R2 C2 plus R1 C1 plus R2 C12 plus GM2 R1 R2 C12. So now you have your tau 1 and tau 2. Now what we are doing, we are taking the ratios of tau 1 and tau 2, which is omega p2 by omega p1. So this will give us okay, C1 C2 plus C1 C12 plus C2 C12 into R1 R2 by this whole square. So this was tau 1. So I'll directly write like tau 1 whole square. So this is the ratio. Now, and this is known as x. So again, you know the value of x. It is a naught square minus 1 by 1 plus a naught cos phi minus 1 plus a naught cos phi. And here your phi is given to be 75 degrees. A naught, you know, it is GM1, GM2, R1, R2. So by substituting this value, we will get the values in terms of, like we have to find x as a function of C12. Now this C12 is not the C12 that we know. Okay. ये जो C12 यहाँ पे हम calculate कर रहे हैं, now it has changed to C12 dash. So ये जितना भी C12 है, these are all C12 dash. Okay. These are all C12 dash. And where C12 dash is actually CC plus C12. Because this is the value that you need to calculate, CC. You don't know the value of CC, right? So these are all C12 dash. C12 dash के terms में you will get a quadratic equation, and you know the value of x already. X is known to you. So now after calculating the C12 quadratic equation, the values that you will get for C12 is minus b plus minus root over b square minus 4ac by 2l, the solution of quadratic equation, with a being 625487884343.53, b being minus 2.288 minus 2.28809, and C being minus 1.3834 into 10 to the power minus 12. Now 74 के लिए, for 75 degrees of phase margin, you did calculate x, right? X यहाँ पे calculate किया था ना? We already calculated this x, 810.98. So we will use that same x here, that is 810.98 degrees, and by using that we will calculate the C1 dash, and from there this is the value of C1 dash that we will be getting, and here the C1 dash is CC plus C12. So the CC will be C12 dash minus C12, and this is given in the problem. This you calculated. So ultimately your CC will be the subtraction of these two, and ultimately you get 4166.398 femtofarad as the capacitance, that is compensation capacitance for your circuit, or 75 degrees phase margin with a compensation capacitor. Clear? Did you understand the flow? How we solved one by one? Is this clear?
Yes, ma'am. Could you please continue, ma'am? There are a few more problems.
Okay. So now another problem is, so in this problem, it is similar to the last problem, but there is one thing that you have to do. In this case, it is, so there we introduced a capacitor, right? CC. We introduced a capacitor CC. In this question, you have to introduce a capacitor CC with the series resistor RC. Okay. So here a CC with RC is required. So a resistor is to be placed in series with the compensation capacitor to calculate out to cancel out the zero caused by the short circuit current. Now, which should be, what should be the value of this resistor? So here you already like the capacitor value is fixed. So CC, let it be CC. Your CC is fixed. It is 4166.398 femtofarad. Okay. Your CC is fixed. C12 is given. Now what you have to find is RC. So again, you'll go through this similar formula. And now we are talking about zero compensation, right? Cancel out the zero. So here we are not talking about the pole, rather we are talking about the zero. So the right hand side zero value, or RHP zero, is given by GM2 GM2 by CC upon 1 minus GM2 RC. So this is the formula that is given, like this is for the compensation capacitor as well as resistor, the zero value that you will get. Okay, so GM2 by CC upon 1 minus GM2 into RC. This is again explained in the lecture. Please go through the lecture. If you don't understand, let me know next time. So from where we got this formula, it is explained. Now here the idea is your zero should be at infinity. So basically your zero is cancelled out. So it has like almost it has been shifted to infinity or it has been cancelled out. So in that case, what you will do, you will get like 1 upon GM2 RC dash or RC is equal to 0. So which gives you RC equal to 1 upon GM2. So like GM2 was mentioned as 1028 microsiemens. So the value of RC is 972.762 ohms. So this is the resistor that you will need to cancel out the 0 and to move the 0 far away from your dominant pole. So that's why we have made the 0 to infinity. Like your 0 has been shifted to infinity. So for that case, we have calculated these values, and this is what we have found out. Clear? So yeah, these all were the problems which were there for today. Please go through them. Yes.
Could you please conduct one more live session? I have doubts, particularly from week 7, few questions, ma'am. In between.
Maybe we can discuss in next week. So next week I'll not keep much of the content, and next week, since it is the last week,
Yes,
so
ma'am.
we'll focus more on the doubts rather than solving problems.
Ma'am,
And
next
most
week
of the concepts are covered already. Next week there is one session, right?
Yes, ma'am. But next week, power amplifiers is very important, ma'am. Means you need to discuss
No,
theory
no.
only.
So power amplifiers, there are no problems on power amplifiers, I guess.
Already question, and today week 12 content has all released, ma'am. There are a pretty number of questions. Means if you conduct question, would be very convenient for ma'am. Very for final exam also, ma'am. In between. I mean, at the end of the live session, I will ask any doubts and all. With the upcoming Monday, in between any Friday or Saturday, with your free time.
No, so the thing is there any problem based on power amplifier? Because last time when I conducted the session, power amplifier was not covered. So that's why. In this
Yes.
week, did you people get any problems on power amplifiers?
Not now, ma'am. Means week 12 we have power amplifiers. So there are pretty number of questions. I just go through the content also.
Okay. So because it was not there last year, so maybe we
Yes,
can
ma'am.
see.
Yes,
And
ma'am. There are pretty number of questions.
We'll focus on doubt clearing session next week.
No, ma'am. You discussed based on week 12 also. Week 12 also is important. Now, power amplifiers, how that phase angle, or how in your fashion, it would be very helpful, ma'am. It won't disturb our doubt clearing session. If you conduct one doubt clearing session, specifically, everything will be gone, ma'am. I mean, we can clear doubts much more.
So for final week, I'll let you know what type of questions were there, because I conducted the same session last year also. The problems.
Yes, ma'am. I attended last session last year. Yeah.
There was no power amplification session as such. Like power amplifiers were not conducted. It was more on Zener diode and those things last time. Yeah, it was more on Zener diodes and regulators. Those type of questions were there. Power amplifier based questions were not there last time. So yeah, maybe I'll see if there are any, but so lectures might be there, but problems won't be there. And even I guess you will not get power amplifiers in exams also, if I'm not wrong. So
Ma'am,
power
could you please
amplifier.
explain about final exam also, ma'am, how to prepare and all? Because I'm appearing, the score will be very useful for TA also. Texas Instruments is associated with this course. That's why.
So power amplifier. So for final exams, you have to go through the lectures, and basically you have to have your concepts very clear. And based on what is taught in the lectures and how you are solving your practice problems, like these tutorial problems, those type of problems only will be there in the exam. Most probably. So it won't be like anything won't be coming out of your content which is taught in the like sessions. Most of the time, everything is covered in the sessions, and those topics are only taken for, taken up for exam. And basics should be clear: how to solve, what is being asked, and yeah, since time is also a constraint, so as we have discussed many times, like there are few shortcuts that you can use to find, let's say, the output impedance and all these. So you can practice those type of problems so that you don't give more time while doing the calculations. So yeah, mostly concepts should be clear to you. Concepts are very important. Otherwise, you will get the problems the way you are doing in these sessions. So these type of problems only will be there. So nothing more than that. Yeah, you can practice these problems, go through the lectures, and it will be okay.
Ma'am, could you, if possible, could you conduct one more live session, ma'am? Means it not disturbing the week problem solving session in
I
between.
mean,
I mean, and much more specifically, I have doubts on a few weak questions, ma'am. If I want, I will tell out that question number also, ma'am.
so, didn't you get the solutions for those questions already?
Yeah,
Which are
yes,
like
ma'am.
3 questions only, no?
Ma'am, I get the solution, but means the approach should be very fine, ma'am.
We have touched upon the approaches, right? So you can solve
Yeah.
in your own and tally your results. That way
Yes,
you
ma'am.
do.
I mean, based on a approach, I'm able to solve majority 70% questions. I'm able to do, ma'am.
Yes.
In week 7, much more specifically, there you cover. I didn't cover 2 questions, ma'am, based on the percentage of error like that.
Percentage of error is not that important. Like it's not a very important type of a concept, so that's why I left it. Like it's not that important, and those type of questions rarely appear in exam, like percentages and all. Majorly, the problems are focused on these all, like pole zero compensation, pole zeros, finding their values, all these steps. The pattern that we have taken up in the tutorials, majority of the times the questions come in these patterns only. So yeah, that's why I didn't take up them.
Okay. Means if you conduct a session, I will. I mean, I'll stress more on that the questions, ma'am. That's why.
Because so I have to see if I can, like I have certain
Or else, can I mail that specific questions, ma'am? Could you please give a detailed solution how you given this in the session?
okay, maybe I can do that.
Okay, ma'am. I mean, I will mail that questions what and all I am facing difficulty. Please help me.
Okay, sure.
Now,
Right.
ma'am,
You can also write to the write in the forum or to the main TAs also, so they can also help you with the
Ma'am, one more thing,
if
ma'am. My
any.
question paper will be given by Chatterjee sir only, no?
Yes,
Or
sir.
else means our NPTEL team will give.
I'm not very sure about that, but I have taken up a course, and what I observed was, so it was a Python-based course, and the problems which I got in the exam were similar to how we used to solve in the tutorials. So problems were very similar. In fact, the terminologies and all were also very similar. So I realized it might be set up by the same faculty because the terminologies and everything are used by a similar person to person differ. So it might be like it should be Chatterjee sir on will be giving the exam. But anyway, it doesn't matter that much. It is more about how clear your concepts are. If your concepts are clear, you can do it anyways. You can solve the problems.
Okay,
Yeah,
ma'am.
but practice more problems, and yeah, you won't be getting a scientific calculator. So you have to use a on-screen calculator over there. So keep that in mind. And yeah, so that on-screen calculator needs to be used. Other than that, yeah, you can go ahead and solve the practice problems like these tutorial session problems thoroughly. And I have also taken up problems from some other sessions also. So it has basically increased the number of problems for you. So you can solve all your problems and all the problems, the
Ma'am,
new problems I have added, and that will do. Yes.
ma'am, can I mail you my queries because I don't want to disturb others. Primarily because the calculation derivation of the your formulas at times is very difficult to memorize. Rather than if you keep the derivation in the mind, it is easy to implement.
Yes. So that's
So
why, see, whenever I have majority of the times I have, like, if they are short formulas, we have derived in class already. We have derived in the sessions. But for the formulas where I have said like you can refer to the lectures, is because there are certain formulas which are derived, like they are lengthy formulas, and they have already been discussed in the lectures. So you can refer to them, and you don't sometimes you don't have to memorize the formulas that much if you know that how to initiate, because step by step ultimately you will reach the formula. So that initial step, what are the assumptions that need to be taken, if you know that, you will get to the formula. That will do. So
ma'am,
yeah.
especially for RDAs, this many a times it is not considered in the formulas.
RDS, yes, RDS, like it depends. If, like, see, that's what I said. RDS, when you consider, when you don't consider, if lambda is zero, you will never consider RDS because there is no factor of RDS. But if lambda is like non zero, then you have to take the factor of RDS. But then, too, if lambda is very, very small, you can neglect it. But if lambda is like, let's say 0.1, 0.01 also we have considered, 0.15, 0.015 also we have considered sometimes. So it also all depends on the assumptions that are being made in the problem, and how far can you neglect some things. So see, if you don't neglect also, you will get a certain answer. If you neglect few things, take assumptions, your calculations will reduce, you will get another answer. But the thing is, how much is the difference between your exact value and your approximated value? If they are close by, you can go with the assumptions. So that's why, to get that idea, what you need to do is you need to try and solve and see, okay, how much is the error that you are getting. If the error is tolerable, then you can go and do assumptions. But if errors is like too much, 10 orders, 20 orders, you cannot, like 10 times, 20 times, you cannot go for those assumptions, right? So that is the basic idea. That's how the assumptions also work. So sometimes we say, okay, these are the assumptions you can take. The assumptions which are like said, this can be taken, are keeping in mind that your error values are low. So that's how the assumptions are made. But without assumption also, if you will go ahead, your calculations will definitely increase. It will become more complex, but ultimately you will get the answer and it will be very close by. And most of the times the answers are not very close by. See, most of the questions you will be getting are MCQs, right? Or numerical answer type. So in MCQs also, the answers are not very close by sometimes. Very few times it is like every answer is like very close to one another. There it is very difficult to tolerate a very small error also. But otherwise, there is certain range in which you will get the answer, so you can get the clue from there. And numerical answer type, so there is a huge range which is given for acceptable answers, so it is not an issue.
Now, ma'am, one more thing. Today, this lecture, you are talking about poles and zeros.
Yes,
Uh, Ma'am, in the first and fourth quadrant, I mean, on the when it is positive, positive, and positive, negative.
yes,
First and fourth quadrant.
yes,
You say j omega and this one.
yes.
No, just above this, ma'am. I mean,
Nahi, I got it. You are talking about S plane. S plane, right?
yeah, ma'am.
Yes. Okay,
Yeah,
so
there you are. There you are. Now,
yes.
this first and fourth quadrant, you said this is an unstable system.
These are unstable systems, yes.
So you have to consider only on the second and third quadrant. I
Second
mean,
and third quadrant, or only imaginary will also do. So that's what I said, right? These are marginally stable system. On the imaginary, if you get only imaginary poles, these are marginally stable system. Otherwise, on the left hand side, they are stable. Now, how left hand side they are, how far in the left hand plane they are, the more stable they are. So that is how, like, they're shifting, right? So how far they go in the left hand side, the more stable they become. So that is the idea. But the moment they are in right hand side, they become unstable. And I explained also, like, why they are like this. We have seen this positive feedback system, no? So in this positive feedback system, if we observe very carefully, the values of your S will always turn out to be positive. Right? And when we say positive as, what does that mean? It is basically the real part which is positive, right?
Yeah.
Imaginary can be positive and negative, but the real part is positive. And the moment the real part is positive, it is actually on the right side of the plane.
Yeah.
And that's why the system becomes unstable.
But do you think that in a third quadrant, which is all the values are negative,
Yes.
that will be more stable system, or the second quadrant?
No. So this is not how we can decide. Why? Because when you are saying something in a second quadrant and fourth quadrant, see, it is a complex plane, right?
Yeah.
So if something is there in a second quadrant, there will be an image or a mirror image on the third quadrant as well, because you will get, when there is a complex solution, you will get conjugate pairs, right?
Yeah, complex conjugates.
Complex conjugates. So if I have P1, I cannot have a P1 in the same quadrant. The P2, like P1 is in second quadrant, so P2 will definitely be in third quadrant because of this complex conjugate system. Correct?
Yes.
So it will always be like, if you have anything in second quadrant, it will have a mirror image in your third quadrant also. So that is always there. Yeah, because of this complex plane. So that's why I said this is not like a simple XY plane. Rather, it is a complex plane. And when you get complex solutions, you always get them as a complex conjugate, right? Or otherwise, you'll get two real values. You can have two real values separated. That is possible. But they will lie on the same axis, real axis. But when you have imaginary, they are always in pairs and they are complex conjugates. So, yeah. So there you cannot decide. So that's why it is said, like, S plane, left hand side solutions majorly stable, right hand side solutions unstable. And in left hand side also, placement of the poles plays a critical role, because let's say if there are 3-pole system or 5-pole system, all the poles are in left hand side only. But where the poles are, based on that you will get the phases, and from there you will calculate the phase margin, and you might come across that the phase margin is like going beyond 180 degrees. So system has already become unstable. Like uh, like all the poles are in left hand side, but still the phase margin has gone beyond your 180 degrees, which is the limit. So which will introduce you the instability. So that is also possible. But the moment there is a right hand side pole, it is definitely an unstable system. So no need to give a second thought about it, because if there is a positive feedback or right hand side pole, it can never be stable. And that's why these positive feedbacks are only used while designing oscillators, because oscillators are unstable systems and they use positive feedback. So they can never be like stable. And when I say stable, I'm talking about this bounded input, bounded output, this thing, right?
Yeah, that's right.
Yes.
But these equations can be correlated with the PI, proportionally integrated PID loops and all.
Yeah. So see, this
Yes.
stability concept that that I discussed today, you can. So this is same that you observe in your control systems.
Yes.
This is how you study stability in control systems as well. Everything is same. It's just that here we are talking in terms of amplifiers and oscillators, these things. There we talk about controllers. But the thing is same. Ultimately, they are also circuits. There also you analyze the things in the same way. It's just the name of the circuit is different. The functionality for which the circuit is used is different. But the circuit is same. The idea is same. The concept behind is always same. So this stability is like stability, Bode plot, these things you can like these are the things that you use in both analog circuits as well as control systems. So if your concepts from control systems is clear, so you can use the same concept in analog circuits also, because ultimately it is the circuit and the analysis of the circuit. Yeah.
Thank you, ma'am.
Any other doubts? So yeah, maybe you can go through the lectures as well as your tutorial problems. Tutorial solutions are also there, but sometimes if you feel that your solutions that you are solving and the solutions that you are getting as solved problems or solutions you are getting from TAs are not matching, or there are some doubts or some discrepancies, since we are not preparing the solutions, but the solutions and the problems are being prepared by some other TAs. So you can always write on the forum if you find some discrepancies and want justification from them. So they will respond. Like, has anybody tried writing to the other TAs who are actually creating your problems and solutions to clarify
No,
your
ma'am.
doubts?
Actually, they are not responding in a forum, ma'am. I
They are
mean, if you
not
go
corresponding.
through,
No, because that is not correct. They should they should answer to your queries.
ma'am, if you see, there are more than 20 to 30 messages not even responding. Only one to two messages are responding.
Oh, that is not correct. Because, see, we are not designing the problems. So, what happens sometimes when a person designs a problem, they have certain thing in mind. So, according to that, they solve the problems also. So, that's why sometimes the solutions also vary from person to person, depending on what are the assumptions you are taking and how you are moving forward.
Yes, ma'am.
So,
That was
yeah.
that was my confusion, ma'am, because that
Yeah.
was I am facing the
And
difficulty.
that will definitely change, because let's say I have certain understanding and I might approach a problem in a certain way. The other person has a certain thing in mind, certain assumptions in their mind, and they approach it by a different way. So there might be different ways to approach, and ultimately we can reach, may not be to the same answer, but to the similar terms. We not get exact dot answers same for each other, but we'll get close by answers. But yeah, there might be two approaches for the same problem. That's not wrong.
Okay,
So
ma'am.
that
Ma'am,
can be done. But yeah, maybe you can write to the forum people only, because they are best to clear the doubts on the solutions they are giving, because the solutions are being provided by them. So they might have taken certain assumptions, and you can also go through the lectures, because sometimes each faculty has certain assumptions in their mind through which they solve the problems. And if let's say Chatterjee sir is teaching and Chatterjee sir's students are only preparing the problem, right? So they will take the same approach. So in lectures, you might find those assumptions which are being made by Chatterjee sir. So that will also clear your doubt.
yes, ma'am.
If
Ma'am,
they're not
I will go through it, ma'am. I mean, I have only 4 to 5 questions exactly doubt, ma'am. Rest of
right,
them are clear, ma'am. I mean, I will mail. I mean, I will work on it for 2 more days also. If I face a difficulty, I will write a mail, ma'am. Could you please provide a
yeah,
detail to this?
sure. If I can solve it, and I also like if I understand and I'm able to solve it, I'll definitely let you know. Otherwise, but it is better you can write to them as well, because they
Yes,
are
ma'am.
sometimes few solutions are not even clear to us also, because the solutions are not that explained very clearly, and the assumptions are not mentioned very clearly, so it is very difficult for us also to understand. But yeah, you can definitely write it to them. And
Ma'am, one
Yes,
more thing.
yes,
Ma'am, when you take a 3D view of the MOSFET for the calculation of areas, for the, what you call as a
we we
junction
did,
capacitance.
we did it last time,
Yes,
right?
you have done
Last,
it. Yeah, we have done it. I'm not saying anything to that. What I'm saying is, ma'am, you know, if you see the 3D view of it, if I'm correct me if I'm wrong, width and the length, one side you have taken one time only. That's okay. That because they exposed
Ah,
to air.
yes,
Other part of it, other angle, that is the not depth, the width into length, not length. What you call as a width into that
depth.
depth. Yeah, the other
Yes,
side of it, another exposed to the air. I mean, exposed to the this one. There are two planes. Correct. There are
yes,
overall 6 planes. Correct. The one, two,
yes.
three, four, five, six.
A
Correct. There are six
cuboid has
planes.
6 planes,
Yeah,
where
but
the
that two
top
planes are,
plane.
I think two planes are not in junction with other four planes are in PN junction, correct? The two planes, which is one on the right, sideways, one is the side, one on the top.
Yes, yes.
Ma'am, correct me if I'm wrong. That second plane also we have considered because that is
Yes,
not.
yes. So see, what happens is top plane will definitely not come
Yes,
into picture
I
because
agree, I agree,
top
I
plane
agree.
has the metal contact.
Correct, correct,
But
correct.
other than that, what is assumed is that your MOSFET with that 5 remaining faces, it is considered that all 5 faces will have that junction formed, and all 5 faces are part of your MOSFET itself. Because after your source, you will leave a certain area and then you will divide it and design another MOSFET. So, with that assumption, when you go ahead, you will have 5 faces. But suppose if you say, no, I'm not using that last phase, I'm terminating immediately over there, I am terminating it with, let's say, an insulator and designing another MOSFET beyond that. At that particular case, you will not consider that 5th phase. But majority of the times, if it is a single MOSFET, so single MOSFET may you don't need that division, right? So you will have that 5th phase. So that's why that calculations that we have done, we have considered all 5 phases. Are you getting my point?
Yeah, getting your point. But then
Yeah.
my point was the one plane which is on the no, not on the top. That is okay. That is exposed.
Yes, on
So
the
I'm
side.
not talking about that. The one which is on sideways,
Yes, yes.
sideways. We have to consider that plane also. You mean to say?
Yeah, yeah. We can see it. That is what I'm saying. It will depend. Now, if it is a single MOSFET, you have fabricated that MOSFET. It is the single MOSFET. You are using that MOSFET, and that MOSFET has that surface like exposed. So there definitely there will be a junction formed, and that
Okay.
junction will contribute to your capacitance. So
Okay.
that junction needs to be considered.
Okay. Okay.
So that's why we considered that.
No, no, I'm just clearing my
Yeah, yeah.
doubts. Man.
No, no, it's okay. So that's why we consider. But now, if let's say it is fabricated such that that particular phase, rather than leaving it for a PN junction, if you are terminating that phase with the insulator or something, so now at that point of time, there is no junction present for that end phase.
Yeah, that
So
is
if
phase.
there is no junction, then no capacitor or no
Okay.
capacitance. So that is the idea. But considering like it is an isolated MOSFET. So if it is an isolated MOSFET, you will have 5 phases.
Okay.
Yeah. So that extra area will come into picture. Okay. So yeah, maybe we can break over here and
Yeah.
we'll meet next week, which is the last session, and we can clear our doubts. Meanwhile, please write to the forums if you feel there are any discrepancies in the solution or something that you don't understand in the solution, or something is like not correct, because sometimes see human can do errors, so there might be errors, so you can write in the forum to them. I hope they answer, but I was not really sure they don't answer to your queries.
Ma'am, because if you want, I will show you, ma'am. Now itself, I can share my screen.
No, but
No,
it's
no, no.
okay. Like, because even Chatterjee sir also tells in the lectures, right? Like, if you have some doubts, write in the forum. In
Yeah, yes,
lectures
ma'am.
also he mentions that. So that's why, but I was not very sure because I've never uh, approached the forum. But yeah, okay.
Ma'am, if I am, I mean, I will post my doubt in forum as well. Ma'am, I mean, after not getting any response, can I mail my doubts, ma'am? Could you please
Okay.
give me insights of it?
Okay, sure.
Yeah, that
Yeah,
was.
we send you the mail, ma'am. I mean, whatever doubts we have, or where it got stuck up, or we are not getting answers, or answers are a little weird. I mean, doesn't match, or the formulas even for the derivation point of view. Because if you remember all those formulas, slightly difficult. Because if you know the crux of the problem, you can easily find out. Write it in exam. That's what the point.
Okay. No, but I think like memorizing is not the idea behind any exam. It is more about the concepts being clear and are you able to solve the problems. Memorizing is not majorly the part as far as I understand from examination point of view. But yeah, maybe you can.
Even Mr. Chatterjee sir has also has indicated in one of the lectures you should memorize these few formulas because the formulas are a bit complex and has involved a lot of parameters.
So that might be the case that the formula is way too complex for you to solve. Like if a formula takes you 2 hours to solve, so you will will you leave your exam for solving a formula, or rather you will leave that question and go for another? So that is the idea, right? So those type of things. But for exams, these type of too complex things will never be a part of an exam. It is more to check your concepts and your knowledge rather than memory based things. So yeah, that is what I understand is the main purpose of exam. But yeah, meanwhile, you people solve it and see what are the things. You go through the lectures also because sometimes, like very few times, I have mentioned that you can go through the formula in your lectures. Otherwise, we have solved the formulas. I have told you the shortcuts also how to get to the formulas, right? So you can implement those things and you will get a reasonable answer, like not exact but reasonable, so you can get your answer because you will have certain range. So in that range, your answer will fit and you'll get the answer. So yeah, with that maybe we can break over here and meet next week. So that's all for today. Thank you,
Thank you,
everyone.
ma'am. Thank you.
Thank you,
Bye.
ma'am. Thank you. Thanks
Good
for your
night.
time.
Thank you. Bye.